We will now turn to our second talk of the session. Our second speaker is Thomas Woodson. He is Associate Professor of Technology and Society at Stony Brook University. His perspective and expertise on the study of inequality is both national and global in scope, and he is focused on emerging technologies, science funding, STEM diversity, and engineering education. Thomas.
Great. Hopefully you can hear me okay. First, I want to thank you so much, Bill. I always enjoy hearing you speak, and I was furiously taking notes as you're speaking, and also want to thank you for your service to science policy. I'm so glad you're in the room because we need more people like you in the room discussing these issues, and so I do thank you for that. Let me share my screen, 1 second. So again, my name is Thomas Woodson. I'm an associate professor at Stony Brook University. I've been there since about 2014 now, and I do thank you for this chance to come speak to you today. So as you know, we have global challenges. You can kind of list them: climate change, inequality, war, population challenges, pollution, privacy issues. And I'm sure that you can think of your own 6 to 10 more global issues that we're facing right now. So I think engineering is a major part of the solution. It's not all the solutions, but definitely engineering will play a major role in solving all of these different challenges we face. So engineering must be inclusive. We have to have an inclusive innovation. I believe you cannot solve global challenges with solutions created in wealthy countries by wealthy scientists for wealthy people. We need people from all over the world, from diverse backgrounds, solving these problems. And so today I hope to discuss some of these inclusive innovations and kind of share some of my experiences in this field. So kind of my background, I started off as an electrical engineer. So as a kid, I was very much interested in math and science. So I was interested in, Popular Science magazine. I had that on my bookshelf. So I really love reading Popular Science magazine. And then also there's this movie called Minority Report. It probably came out 20 years ago or so. And in that movie, Tom Cruise was moving things with his hands on the screen. And I thought that was the coolest thing ever. And so that made me want to become an electrical engineer. And so in undergrad, I studied electrical engineering. And probably in my third year of engineering, I had a chance to go to a developing country to help set up a research lab. And every day at 2 p.m., the electricity was cut. And as you can imagine, no matter how talented of a scientist you are, if there's no power at 2 p.m., there's only so much work you can do. And so that really made me get me started thinking about science and technology policy. And so that's why I pursued that for my PhD. And right now I'm in the Department of Technology and Society at Stony Brook University. So right now I study a lot with inclusive innovation. Yes, just 1 second, I can get 2 slides. There we go. I study inclusive innovation and do many different things. One area I study is nanotechnology. I think Bill talked a little bit about that, this national nanotechnology initiative. I was a product of that. Some of the funding for that initiative went to my studies. And so thank you, NSF, for that. Another area I study is science funding and how we can improve science funding, especially for countries around the world. So let's say Vietnam, right? How can Vietnam improve their science funding to be more innovative? Or how can Ghana or South Africa and countries around the world improve their science funding and science infrastructure to be more inclusive and more innovative? I also study big data. A lot of my research now looks at some of these new algorithms. How can they be more inclusive? And later on in the presentation, I'll share some observations about kind of inequality in big data and in these big data algorithms, artificial intelligence. And last, as Jeff mentioned, STEM diversity. How do we increase the number of people and types of people involved in STEM fields? And so we want people who are, some people are kind of naturally talented in math and science, and they say, oh yes, I want to be an engineer. But many people discover, hey, it may not be their natural talent to be in science and engineering, but they have some of the skill sets and talents and tools to be great engineers as well. And how do you get those people involved in STEM fields? And how do you get people thinking about systems thinking? So even if you're not a professional engineer, thinking about how do you approach problems like an engineer, or even how do engineers approach problems? Because engineering is all around us. And so if you want to be able to function in this world, you need to understand how engineers think. So one project I was looking at was this broader impacts. Excuse me, one second. My slides are a little jumping all over the place. There we go. Yes, I've been studying broader impacts recently. And so since about 2018 or 2019, I had this grant from the National Science Foundation to really study this broader impacts of funding. I developed this thing called the inclusion immediacy criteria to really break down broader impacts and find new ways to categorize them. And so this framework has two classifications. One's called inclusivity and one's called immediacy. And I don't have a lot of time to discuss this whole framework, so I have that citation there if you want to look more into it. And of course, you can feel free to contact me at any time. We can talk more about it. But what I was trying to do and understand is that these broader impacts affect people differently around the world. So for example, some innovations affect people globally or universally. So if there's a solution to climate change, for example, that'll help you regardless if you're rich or if you're poor. So that's kind of a universal benefit. Some innovations are really geared towards the advantage, or at least the status quo. So if someone develops a new fighter jet, obviously that's a great innovation. That's mostly geared towards the advantage communities, the military, people with money. So that's kind of that segment of society. And some innovations are towards that segment of society, but that's really helping the advantage groups. And of course, there's some innovations that are geared towards marginalized communities. They're more inclusive. So if you develop a new malaria vaccine, for example, that would be an inclusive innovation. Also, some innovations are, in terms of immediacy, how do you achieve these broader impacts? So sometimes the broader impacts are closely related to the research itself. So again, developing a malaria vaccine, the broader impact and the innovation are tightly linked. Some broader impacts you kind of achieve while conducting the research. And a great example is actually training students. So many of these research projects, they actually, in order to get this work done, you need a whole team of students to do the work. And so as you're doing the research, you're actually training new generations of scientists. And that's a direct benefit of broader impacts. Well, I want to highlight two interesting research topics. As I was doing my studies, I found that this is a very good broader impact. One is called the nature-based solutions for restoring rivers and streams. So as we all know, many of our rivers and streams are very polluted, and humans are a big part of that pollution. And so because we're polluting these rivers and streams, it's having a big impact on the environment. And so this researcher is trying to find nature-based solutions to restoring rivers and streams. So as you can imagine, one way to do that is by planting trees or having other wetland structures. And if you do this correctly, you can really transform rivers and streams and make it sustainable. But what I really liked about this project was that it wasn't just one discipline. It really brought in information from, let's say, civil engineering, mechanical engineering, computer science, because they're actually modeling the structures, the best structure that you can use to restore these rivers. And so should it be a square, should it be a circle, should it be very tall? What's the shape of this structure? And so they're actually using computer software, computer algorithms to develop these new shapes. And I thought this was a very good example of a project that has tangible benefits that you can see immediately, but yet it brings lots of benefits from across engineering fields to work on this problem. Another good example would be this one on cyber. I'm sorry, there we go. This is right here, the cyber infrastructure. So reliability and resilience assurance of cyber physical energy systems. And so many of you remember in 2021, there was this Colonial Pipeline attack. And so in the Southwest, this pipeline, they supply gas to the region, and they had a hack, and someone held their data, held their billing system, so they couldn't supply the energy to the people. And all of a sudden, this caused a huge issue. I mean, there was long lines at the queue. Planes were canceled, flights were canceled. There was no gas. And so as a country and as a world, we need to think about how do we secure these critical infrastructures. This is especially important as we develop new types of clean energy, solar and wind, and merging these things all together. If we're not very careful, it'd be very easy that we don't mesh those systems together safely and securely. And so I thought this was an interesting project, thinking about how do we best secure our cyber physical infrastructure. One second. There we go. So I mentioned two major impacts, infrastructure or clean rivers. But many of our broader impacts, the impacts of engineering, actually occur at quote unquote smaller levels. Here's 4 examples. One is teaching. Many of these grants are placed at universities. That's where a lot of this National Science Foundation funding happens, is at universities. And teaching is a major goal of these universities. And so a lot of the research that comes from this funding goes back into teaching. Better courses, better understanding of how do we teach students, updating the curriculum so that we're not about, telegrams, we're talking about, AI and the future of AI. And so these things are incorporated into the classroom, a major, major impact that sometimes is overlooked. Also collaborations, having people from across the world working together on these problems. So, one second, make sure the right side, there it is, right, that's the right slide. So first I said teaching, and then I'm talking about collaborations. And so again, many of our, these projects have international collaborations, making sure we're working together with people around the world. And again, the NSF in the USA is very unique, it's a very large system. And we have the power and the innovations to really communicate, collaborate with people from around the world. And so collaborations are another broader impact that can be easily overlooked, but it actually is having tremendous impact in the world and science around the world. Next is training students. I talked a little bit about this before, but again, many of our projects, we need students in order to get these projects finished and accomplished. And so training students, we really are developing the next generation of scientists. And if you look at NSF grants, in my study, about 70% of the grants have some component that's training students. And so a lot of the money is going towards training students in the next generation of scientists. And of course, science infrastructure. We can think about the big infrastructure, let's say the colliders, those are these big infrastructures, but there's also small infrastructures, a microscope, data sets. All these things are so important to development of science. And again, scientists from around the world can use this infrastructure to do their own science. And so if you're a scientist, let's say in a local country, you may be able to use this scientific infrastructure to do your own research. And that's very powerful. But like lots of science and technology, you gotta be cautious. I'm cautious with engineering. And I'm running out of time, but I wanna highlight 3 big kind of disasters. The first one's the Titanic. We all know about the Titanic, the biggest ship that was ever built at the time. It hit an iceberg, it crashed. There's been made about this. And it was the most deadly passenger ship disaster at the time. And when the Titanic was built, it was really a marvel of engineering. They had to develop new propulsion systems, new communication systems. How do you make sure there's enough food, water for the passengers on the ship? So an amazing technology. But again, I think the challenges with the Titanic was the hubris. They got so confident that they could never sink. And I think engineers need to be cautious. It's easy to think that our solutions can solve all the problems. It's easy to be kind of lulled into a false sense of security by our technology. And so really thinking about the safety and some of the other challenges with technology is very important for engineers to do. Another example is this kind of the story from the BBC. This happened a few years ago. Google apologizes for Photos app. So in this story, about 5 years ago, Google had this software that was identifying pictures. So you could see, okay, this picture is of a dog, and it'd say this is a dog or a cat, or your friends, it'd say, okay, this is Mr. Smith or John. And so that's what this app was doing. And so, but unfortunately, people with darker skin, they didn't they didn't model the algorithm well enough. And so that it was actually misplacing people with darker skin for gorillas. And so as you can imagine, this is a huge blunder that was going on. Now, I'm not just going to pick on Google. This is a kind of a major issue across all these platforms, across all these algorithms. How are they developed and how are they tested? A lot of the biases that are in society are built into these algorithms. And so you're going to find many problems, whether it's with policing in prisons, whether it's with your credit scores. These algorithms are everywhere. And so engineers need to be very cautious with building these new algorithms, develop this technology, so that way it doesn't have unintended consequences. A last example here I want to give is about women trace tech gender gap to childhood. And so again, this is a story that has been in the news for the 50, 60, 100 years. Why isn't STEM fields more diverse? Why is it the same people in STEM? And how do we get women and minorities involved in STEM? And this is a continual challenge of engineering. And I think many great minds are working on this. I know Bill has been working on this in the past, and many people in this panel will be talking about this are in this research, but really thinking about how we improve engineering to make it more inclusive. So now what? I like to kind of close with some final thoughts. One thing you could do is become an engineer. Many people listening to this may be students, kind of thinking about where to go as a career. Other people may be looking for a second career, and so really thinking about becoming an engineer. But again, for many people, it may not be possible for you to spend 4 years in undergrad or in graduate school getting an engineering degree. But I think you should understand, at least understand engineering and how it works. Understand systems thinking. The world's complex. You pull in one thing, something else will move. So understanding how engineers approach the problems could be very useful, even if your main job is not to be an engineer. Also, I think you should think about inclusive innovations. How can you make innovations more inclusive of everybody? Rich, poor, black, brown, white, green. Everyone should be involved in innovations. Again, as I mentioned in the very beginning, we have global problems. And in order to solve these global problems, you need people from around the world to solve those problems. You can't solve climate change with just people on, as Bill was saying, the two coasts of America. We need people who are in the middle of the country, and really people from all over the world, people from Africa, South America, to solve these problems. And of course, diverse inputs. People from different backgrounds have different ideas how to solve these problems. And those are very crucial to engineering as well. So with that, I'll stop and I'll open up for questions into the panel. Thank you so much.
Thank you so much, Thomas. A wonderful talk. In thinking about both broader impacts and also large, I guess the ideal is to integrate broader impacts with scientific projects. But you also talked about in a paper the possibility of projects that are just focused on broader impacts. For instance, more like set aside, like the EPSCoR program, where there's buckets of money. And I'm wondering if you could talk about that and the opportunities and the advantages or perhaps challenges with doing that.
Yeah, the broader impacts is I think been a great emphasis for the NSF. When a person writes a grant, they have to talk about the broader impacts of the research. And I think that's important for scientists and engineers to do. It's easy for us to get so involved in the details of a project that we forget, how does this impact the world? And this is especially important for taxpayer money, right? Because this is taxpayer dollars going to fund our science. And so I think it's great that the NSF makes this a priority to show those pesky politicians sometimes that, yes, our research is important and it's really transforming the world. And that's very useful. I also want to say it's also very valuable to have some science that's just for exploration. I think that's a use as well. And so if a pure mathematician wants to explore number theory, sometimes we don't know the impact immediately. It may have an impact, it may not. But the exploration is valuable in and of itself. Just like going to the theater or music. I mean, what's the broader impact of a symphony? Well, it's beauty, it's creation, it's something new and exciting. And I think science and engineering can have that as well. As engineers, we're lucky because engineering by its core nature has impact. We're making something. That's kind of the nature of engineering, that it has a very clear impact. And so I think as engineers, this is focused on engineering, we can make a strong case that our work does have immediate impact. And I think scientists and engineers need to emphasize more. Just make sure it's very clear to the public that we have impact.
In thinking about the visits I did to several historically Black colleges and universities for my FastLane research with Tom, the book was about 5 years ago, but the actual interview is closer to 8 or 9 years ago. And one thing I was hearing in talking to faculty members, scientists, and engineers at HBCUs from some individuals was the desire or the aspiration to graduate up from just getting education-based and smaller grants to larger scientific grants. And in thinking, one area I've done some research is on DARPA's Information Processing Techniques Office and how it created centers of excellence in computing. And some of these were at MIT and Stanford, which were already elites. But one was at Utah. It created a major center of graphics, and that computer science department and graphics at Utah has remained really impactful ever since. And I'm wondering if there have been any attempts to, and I guess another example is NIH funding Howard for certain medical centers, as well as health and human services for research centers. Has there been a model yet or exploration of doing major investment in long-term funding of a big science at one of the historically Black colleges and universities, or one of the Hispanic serving institutions?
Great question. I'm not sure, Jeff. That's something I haven't looked into. I think that's, but your point is so important to make, that a lot of these other institutions have so much to provide for science and engineering. And so really getting funding into these institutions. And so the NSF does have a few mechanisms to do that. As you mentioned, there's EPSCoR, which is for states that don't have lots of resource funding. And then they have the different programs for HBCUs and minority serving institutions. And emphasizing those, getting money into the hands of those professors is so important. Of course, there's other, I'd say, systematic challenges that these institutions face. Teaching loads. This is a classic example. If you go to some of these smaller schools, you're teaching 4 or 5 classes. A faculty member is teaching 4 or 5 classes. And if you're teaching that many classes, you just don't have time to do research. And so I really would encourage policymakers and people who are funding science to think about how can we reduce teaching loads for faculty at these universities so that they can invest more time into doing research. Because obviously they need the time to do it. Also the resources for the infrastructure. So a lot of these smaller schools don't have, let's say, the big laboratories. And so being willing to fund these universities with laboratories and with the microscopes, with the wet labs, with the computing power, that can be very useful to make sure some of the smaller universities, HBCUs, Hispanic serving institutions, have the necessary technology to do their actual quality research that they want to do. So that's always a good thing. But to your original question, do I know of any programs? I haven't studied that myself, so I'm actually take a note for that as well. If that's something add that to my list of things to study, because it is an important topic.